We're going to talk about a framework for product process integration analysis of construction operations using discrete event simulation and BIM.
Thank you.
Joseph Lewis is an associate professor in the School of Civil and Construction Engineering at Oregon State University. He received his PhD and his MS in civil engineering from Purdue, and he has created the Constrobe simulation engine and applies it to simulate and analyze various operations in the construction and built environment domain by integrating it with data sources such as the BIM model, graphic information systems, and real-time sensor data from construction equipment. He serves on the board of the International Association for Automation and Robotics in Construction, a member at large of the Education Committee of the ASCE Computing Division, and is track coordinator for the Project Management and Construction track for the Winter Simulation Conference. Well, Joseph, welcome to PPI, and we look forward to hearing what you have to say.
Thank you, Gary. Hello, everyone. Good afternoon. So my name is Joe Lewis. I'm a faculty at Oregon State University, and I'll be presenting this work that I've been doing with our team here, which consists of my student, Samira Mir Hassani, and my colleague, Hisham Said from Santa Clara University. So the title of our presentation is a framework for product process integrated analysis of construction operations using discrete event simulation and building information modeling. So let's get started. So as we've been seeing in some of the presentations today, it's clear that traditional projects are primarily planned and managed using schedules. And schedules do a great job of defining what should be built and by when it should be built. They, however, do not give any details on how the work should happen. For that, we need to look at the production system on the site. And this is really what determines what can actually be accomplished by considering the resources that are available and the constraints that are present on the site. So in order to deliver projects reliably, we need to, as PPI advocates, we need to model, analyze, optimize, control, and improve project production systems. Now, when it comes to approaches towards modeling and analyzing such production systems in a holistic manner, there have been numerous efforts, and approaches. As you can see, there's concurrent digital engineering, which aims to develop the product design along with process design inspired by other industries. There's also computer-aided production engineering, which tries to integrates processes, products, and resources to provide a full picture of the production system. So our goal is to add to this this growing area of knowledge by presenting this integrated product process modeling framework with the goal of analyzing project production systems. So to get started with this, we start with the five levers of production as defined by PPI. The first one is product design. We have process design, capacity, inventory, and variability. And we try to map it to methods which can be used to model and analyze each of these levers, right? So, of course, product design can be mapped directly to building information modeling. It allows you to create building product designs and analyze it and optimize it. All these other levers can somehow be mapped to discrete event simulation, which is a sophisticated tool that comes out of operations science. And it can be mapped because discrete event simulation allows you to map processes using activity cycle diagrams, which allow you to depict your process designs. Now, capacity and inventory are treated as two different types of resources in these discrete event simulation models. And variability can be modeled using probabilistic distributions in the simulations. So you can see that discrete event simulation really can deal with 4 of these 5 levers. It really does not work with the product information that can come from the product designs. And it is this lack of integration that we are trying to tackle here with this framework. So just want to spend a slide on discrete event simulation because I think most folks would be familiar with building information modeling, and it's more widely adopted in industry as well. So discrete event simulation is a means of simulating construction processes by considering the activity sequence, the resource interdependencies and requirements, and the uncertainties that are inherent in the system. And it enables us to perform a lot of what-if scenario analysis by conducting these parameterized simulations. And you can see on the right side of my screen here, This is a sample process map, which is being run as a discrete event simulation. You see different activities and the resources in these circles or queues. And you can see the inventory flow through the operation. And at the end of it, we can get statistical results and performance measures of interest like idle times, utilizations, WIP, and so on. And we're using the Constrobe simulation software, which is developed by myself. But this was inspired and based on the stroboscope and easy strobe system, which I think folks are familiar with in PPI, which is developed by Dr. Julio Martinez. The advancement that Constrobe has is that it enables automation through the Python language, which opens up access to a lot of different types of data, which is what I'll be talking about today. So with that background, we can look at both of these modeling methods. We have product modeling on one side with building information models. On the other side, we have processes with discrete event simulation. And I mentioned the Python language, and that is really what allows us to exchange data between the BIM models from the IFC format. And we can get we can query and obtain any type of spatial or product data from there. And on the other hand, we have process data that can also be handled by the Python library. Now, in addition to this, we're also visualizing the production process itself using a visualization engine. In this case, we're using the Unity game engine. And here, we're adding one more thing, which is we've programmed resources that are used on projects as smart objects, which have the functionality that you would expect them to have in the real world. So this is the overarching framework. And what I'd like to do next is to just walk through each of these components through the lens of a case study. So just quickly, the case study is of a Bay Area modular housing project, which was completed in 2017. And we just used the plans and the operations from this case study to kind of prove out this framework. It consists of about 416 modules that have been installed in 4 phases. And what you need to know is that the modules were made in a factory, and then there was a laydown yard very close to the final project site. The modules were transported there, and we had a telescoping crane at the laydown yard to load trucks, which would then move modules to be installed in the main building. So we've applied our framework to determine the impact of the number of cranes, the number of trucks, the capacity of the laydown yard, and the installation sequence, which is based on the product design, on the final schedule that we can generate. So here's the building information model, the BIM of the project itself. And this, of course, represents the product design that we're trying to build. It informs the process by providing us with the location and the type of each module. If you look closely, you can see that this BIM model is divided. It shows the different modules that need to be stacked together to complete the project, right? So we can actually query details from each module, any module that we want here, and they're each individually identifiable. And this also constrains the possible locations of the cranes, right? So when we're thinking about where we want to be placing the cranes and what impact that might have on the number of times that we need to move the crane or the duration that it takes to unload a truck and place a module here, that's something that is informed by the BIM model as well. Something else that the product design, the BIM model tells us is we can also start to experiment with, the order of installation or the order of placement of different modules. This again becomes important if the product is designed such that the crane would need to move to different locations in order to be able to place the module in the correct place. So you can see how the product design can inform the process here as well. So here we've used a snake path. You can see that we go from left to right for the ground floor, and then we go from right to left again. So this could have an impact on how many times we need to move the crane. On the other hand, we can also test out what it might look like if they all went in one direction. Here's the process map of the operation, and I just want to kind of show you how we can get all of the remaining 4 levers in this process model again. So this kind of defines the sequence of activities that needs to happen in order for the inventory, which is the module, to go from factory to its final location in the building, right? So we have various types of capacity here. So we have space, which denotes the space in the laydown yard, which is 24. We can change that and experiment with that. We have other critical resources like the crane at the laydown yard and the other crane at the uh, project site. We have trucks to transport modules from the laydown yard to the project site. And in terms of inventory, we have the modules that move through the system. And you can see that, there are queues. The queues are denoted by circles where it could build up depending on the capacity or the lack thereof, right? And variability is shown here through the use of probabilistic simulations, which are obtained in the durations of the various activities. So next we have the resources that we've modeled for this project. So these resources were modeled in Unity, and the two ones that we modeled are the telescopic crane, as you can see here, and the lattice boom crane. So you can see that, if we just provide the crane the with our targets, pick and place locations, the crane can figure out for itself the motions, the required motions, according to a rules-based system. So it would determine how much it needs to slew, luff its boom, telescope its boom if possible, and how much to move the hoist in order to get it to the correct location. The purpose of doing this is so that we can get some more realistic estimates based on the actual physics of the equipment operation for placing modules. Now, of course, we can also build further intelligence into this to make sure that our lift plans that we're generating avoids collision with other obstacles that might be present on the site. And lastly, because we're using this game engine, we can now take this crane and use it for a different project, and it should still work the same. So it's just like how we would do it in the real world. So we've provided these digital objects with the same type of functionality that enables its reuse in different projects. So now when we put all of these things together, which is our BIM model, which represents the product design, as well as our discrete event simulation model, which tells you how resources interact with inventory and constraints, and we put in our resources, we get something that looks like this. So it's a complete digital representation of the work that happens on the site. And we can really start to visualize the processes that we expect to happen. So you can see that here we're using just one truck. So we're moving one module at a time. And you can see how space is, being freed up or being used at the laydown yard. And you see that, these things, they're timed so that they make a logical sense. So you're not going to see the crane move until the truck arrives and so on. So one thing that's really useful about this visualization is it allows, first of all, the modeler to understand that they're modeling the operation according to their own understanding. It also allows us to communicate this model and obtain feedback from folks on the ground, right? So they can tell us if we are missing some a big constraint that they're seeing on the site that the modeler is not seeing. So it's a great way to communicate potential process plans, potential resource uses and such to the folks on the site and to obtain their feedback as well. All right. So this just shows you another view of it. So let me move on. But having said that, let me also just say that the visualization is not the end goal, of course. The end goal is to have the visualization just serve as a communication tool and a test bed that allows us to experiment with changing or experiment with the different levers of production and see how that impacts schedule. So ultimately, what we want to do is we want this system that has the product design with the discrete event simulation to generate the schedule based on the underlying physics of the production system, right? So you can see here, we've generated schedules for three different scenarios here. So you can see if you look at the topmost schedule, we see that we're using a laydown capacity of 24. And when we reduce it to a laydown capacity of 12, so we can store 12 modules at a time, we see that there's no change in our schedule, which just tells you that the laydown capacity is not a bottleneck at all in this operation. The real bottleneck is, of course, the fact that we have only one truck loading one crane. So when we increase both of those, the trucks and the cranes, we've just half the time that we take to construct it. So these are things that we can make these changes. We can see what these changes might look like on the site through the visualization. And then we can get some schedules and metrics as well. So I'd just like to quickly go over another type of the same type of analysis. So here, instead of using product information, we're using spatial information from GIS. So this would be a great way to scale up the type of operational analysis that we can do for one site to more regional sites. And what we're doing here is looking at debris clearance after disasters. So in Oregon, we have counties that are very susceptible to landslides. And the question here is how much resources do we allocate to different transportation depots based on the number of or the susceptibility to landslides. And this is the process model that we have, the discrete event simulation model for the debris clearance of landslides. So if you look at this model, it's a very simplistic model, I'd say. It's just excavators loading debris onto trucks and the trucks hauling the debris, dumping it, and coming back. However, when you scale this up again to a region, it's no longer a trivial problem. We need a methodical and analytical way to explore different the solution space to see where we might want to allocate resources. And so we can start to answer questions for transportation agencies, even for contractors who might have multiple depots and sites as to how they want to allocate their resources. So here's just a simulation showing you how the different colors represent resources from different depots. So how they're being allocated to the different landslides. And this would in turn generate the schedule. So just to conclude, these schedules are being generated by the underlying production system, which considers both the process side of things and the product side of things. All right. So in my conclusions, so just to conclude, right? So what we've done is we've presented this product process integration framework that enables the analysis of all 5 production levers simultaneously to generate reliable estimates of performance. And this framework is generic and can be applied to any construction operation. I use the word any because all the tools here, which is discrete event simulation, GIS, and BIM, are applicable very widely. I guess, most construction operations. The visualization can really help with communication, but that is not the end goal here. The end goal is for it to support evaluation and experimentation with the levers. And really what we want this testbed to be used for is for it to evaluate different strategies. Ongoing efforts include refining crane model behavior and creating more such smart resources so that we can rapidly, if we can obtain a BIM model of an ongoing project, we can quite rapidly generate these types of scenarios. And also what we want to do is with this case study, analyze more levers, more combination of changing all of these levers and scenarios. We're also looking for other industry case studies where it might be of interest to integrate this analysis, looking at both the product, the spatial analysis, and the discrete event simulation. And I just want to end by saying that we don't always need all 3 of these. Perhaps it's GIS and BIM that might be required to answer certain questions, or DES and GIS for some. But of course, if it's required, we can connect all of these and exchange information quite in a seamless manner to generate these types of holistic production analysis systems. So with that, I'd like to end my presentation and thank you all. I'd like to open up the room for questions.
All right, thank you. One quick question for you. Have you looked at tying this to 4D scheduling?
Thank you. Thanks, Gary. That's a great question. So I'd like to just distinguish this from 4D scheduling. So 4D schedules tie the schedules to the 3D model or the BIM model, right? And it shows you the evolution of the building product with time. So what can be expected on day 60 versus day 90. It does not show you the resources, how the resources occupy space and move it, and how the resources need to move, etc. So for that, we need to switch out the schedule with the discrete event simulation. So
Well,
that's the relation.
your work demonstrates once again how powerful DES is and how it can enable decision making to do more with less on projects. So thank you very much.
Thanks, Gary.
All right, we appreciate that.